The universe holds secrets that would make your high school physics teacher quit their job tomorrow. While you were memorizing formulas about gravitational pull and learning that black holes are just dead stars that collapsed, scientists were discovering phenomena so bizarre that they sound like science fiction. What if I told you that black holes don't just swallow everything that comes near them, but actually spit some of it back out? What if the smallest black holes are actually the hottest objects in the universe? What if time itself breaks down at their edges in ways that would make your brain hurt just thinking about it? Tonight we're diving deep into the cosmic abyss to uncover the mind-bending truths about black holes that somehow never made it into your textbooks. These aren't just theoretical curiosities floating in the void. These are real, measurable phenomena that are reshaping our understanding of reality itself. From black holes that form without any stars dying to monsters that devour entire suns for breakfast, the universe is far stranger and more violent than anyone ever told you. Picture this. Somewhere in the cosmos right now, there's a black hole spinning over 1,000 times per second, warping space-time so violently that it's literally dragging the fabric of reality around with it. There are black holes so massive they shouldn't exist according to everything we thought we knew, and others so small they could evaporate in the time it takes you to blink. The 2024 discoveries alone have turned decades of accepted science upside down, revealing formation mechanisms that sound impossible and behaviors that defy logic. But here's what makes this even more incredible. Every single one of these cosmic monsters is teaching us something fundamental about the nature of existence itself. They're cosmic laboratories where the laws of physics get pushed to their absolute breaking point, where time and space become so distorted that our normal understanding of cause and effect simply falls apart. So settle in, because we're about to embark on a journey through the darkest corners of space, where gravity becomes so strong that not even light can escape, and where the universe reveals its most closely guarded secrets. This isn't the sanitized version of black holes you learned about in school. This is the raw, unfiltered truth about the most extreme objects in existence. The first thing your teachers never told you is that black holes aren't actually black. This might sound contradictory, but bear with me because this gets fascinating quickly. While it's true that nothing can escape from inside a black hole's event horizon, the region just outside is one of the most energetic and luminous places in the entire universe. When matter spirals into a black hole, it forms what scientists call an accretion disk, a swirling maelstrom of superheated gas and debris that glows brighter than entire galaxies. These accretion disks reach temperatures of millions of degrees, emitting X-rays, gamma rays, and intense bursts of radiation that can be detected from billions of light-years away. Some black holes are so active that they outshine all the stars in their host galaxies combined. The supermassive black hole at the center of the galaxy M87, for example, creates jets of particles that extend for thousands of light years, visible across the electromagnetic spectrum like cosmic lighthouses, broadcasting their presence across the universe. But the real mind-bender comes when you realize that black holes actually emit their own radiation. In 1974, Stephen Hawking discovered that black holes slowly evaporate by emitting what's now called Hawking radiation. This happens because of quantum effects near the event horizon, where particle pairs pop into existence from the vacuum of space. Usually these particles annihilate each other immediately, but near a black hole, one particle can fall in while the other escapes, carrying away a tiny amount of the black hole's energy. Here's where it gets weird. The smaller a black hole is, the hotter it burns. A black hole with the mass of our sun would have a temperature of about 60 nanokelvins colder than the cosmic microwave background radiation. But a black hole with the mass of a mountain would be hot enough to melt steel just from its thermal radiation. The tiniest black holes would be so hot they'd evaporate almost instantly in brilliant flashes of gamma rays. This creates one of the most counterintuitive facts about black holes. They get hotter as they lose mass. It's like a cosmic furnace that burns brighter as it consumes itself. The evaporation process starts slowly but accelerates exponentially. A black hole with the mass of our sun would take longer than the age of the universe by a factor of 10 to the 67th power to completely evaporate. But once it gets down to the mass of a large asteroid, it would explode with the energy of millions of hydrogen bombs in just the final second of its existence. Now let's talk about something that will completely shatter your understanding of how black holes form. Your textbooks probably told you that black holes come from massive stars that run out of fuel and collapse. While that's true for some black holes, recent discoveries have revealed formation mechanisms so bizarre they sound like cosmic magic tricks. In 2024, scientists made a discovery that rewrote the rules entirely. They found a black hole system called V404 Cygnus that exists as a triple system, with one black hole, a close companion star, and a second star orbiting much farther away. The problem is, this configuration shouldn't exist if the black hole formed from a typical supernova explosion. The violent death of a massive star would have kicked away any loosely bound objects, leaving no trace of that distant companion. This discovery provided the first direct evidence of what scientists call direct collapse black holes. Instead of forming from stellar explosions, these black holes emerge from a completely different process. Picture a massive cloud of gas, larger than entire solar systems, slowly collapsing under its own gravity over millions of years. Unlike the violent stellar explosions we typically associate with black hole birth, this process resembles a cosmic implosion happening in relative silence. The conditions required for direct collapse are incredibly specific. The gas cloud must remain hot enough to avoid fragmenting into individual stars, yet dense enough to eventually trigger gravitational collapse. When these conditions align, the entire cloud implodes, creating a black hole that can be hundreds of thousands of times more massive than our sun right from the moment of its birth. But direct collapse isn't the only alternative formation mechanism that schools never mention. There's an even more exotic possibility called primordial black holes. These hypothetical objects would have formed in the very first moments after the Big Bang, when the universe was less than 1 second old. Imagine the early universe as a seething foam of quantum fluctuations, where tiny regions of space experience density variations far more extreme than anything we see today. In these primordial moments, some regions became so dense that they couldn't expand with the rest of the universe and instead collapsed in on themselves. Unlike stellar black holes that form from the death of massive stars, primordial black holes would have formed when the universe was still a hot, dense plasma before the first atoms had even formed. These primordial black holes could have masses ranging from less than a paperclip to hundreds of thousands of times the mass of our Sun. The smallest ones would have evaporated long ago through Hawking radiation, potentially contributing to the cosmic background radiation we detect today. But the larger ones might still be out there, invisible and undetected, making up a portion of the mysterious dark matter that comprises most of the universe's mass. Stephen Hawking theorized that countless primordial black holes might be floating through the halo of our galaxy right now, completely invisible to our telescopes but exerting their gravitational influence on everything around them. If this theory is correct, then space around us isn't empty at all, but filled with these ancient remnants from the universe's violent birth. The search for primordial black holes represents one of the most exciting frontiers in modern astrophysics. Scientists are using gravitational wave detectors, gamma-ray telescopes, and even studying the subtle bending of light from distant stars to hunt for these cosmic ghosts. Finding even one confirmed primordial black hole would revolutionize our understanding of the early universe and potentially solve the mystery of dark matter. But perhaps the most mind-bending aspect of primordial black holes is what they tell us about the nature of time itself. These objects would be older than the first stars, older than the first galaxies, older than any structure we can observe in the universe today. They would be direct remnants of the cosmic inflation period, carrying information about the universe's earliest moments encoded in their very existence. Recent computer simulations have revealed yet another exotic formation pathway that seems straight out of science fiction. Scientists have discovered that in the early universe, under very specific conditions, massive gas clouds could undergo what they call a bars within bars mechanism. This process involves self-gravitating gas losing angular momentum through runaway dynamical instabilities, leading to the rapid formation of incredibly dense cores. In these simulations, researchers watched as pristine gas clouds, some containing millions of times the mass of our Sun, collapsed and formed supermassive stars that lived for just a few million years before collapsing directly into black holes. These direct collapse events could create black holes with masses of tens of thousands of solar masses almost instantaneously, providing seed black holes that could grow into the supermassive monsters we see at the centers of galaxies today. What makes this discovery so significant is that it helps solve one of cosmology's biggest puzzles. How did supermassive black holes grow so large so quickly in the early universe? Observations from the most distant galaxies show fully formed supermassive black holes existing when the universe was less than 1 billion years old. Traditional formation mechanisms simply don't have enough time to grow stellar mass black holes into supermassive ones in such a short time frame. The direct collapse mechanism provides a shortcut, creating massive seed black holes that had a head start on their growth. These seeds could then continue accreting matter at incredible rates, eventually becoming the billions of solar mass monsters we observe today. Some of these early black holes were so voracious that they consumed matter at rates 40 times beyond what theoretical physics predicted was possible. challenging our understanding of the fundamental limits of accretion. This brings us to one of the most shocking discoveries of recent years that completely demolishes everything you thought you knew about black hole behavior. In 2024, astronomers discovered a supermassive black hole designated LID 568 that's breaking every rule in the physics textbook. This cosmic monster is consuming matter at a rate that should be absolutely impossible according to our current understanding of how these objects work. There's something called the Eddington limit, which represents the maximum rate at which a black hole can theoretically consume matter while maintaining equilibrium between the inward pull of gravity and the outward pressure from the heat of compressed, infalling material. It's like a cosmic speed limit for how fast a black hole can eat. But LID 568 is completely ignoring this limit, consuming matter at 40 times the theoretical maximum rate. This discovery is forcing scientists to completely rethink the fundamental physics of accretion. The black hole is essentially gorging itself at a rate that should create so much outward pressure from heated gas that it would blow away any additional incoming material. Yet somehow this cosmic glutton keeps feeding, growing larger and more massive at a pace that seems to violate the basic laws of thermodynamics and radiation pressure. What's even more disturbing is that this isn't happening in some distant, exotic corner of the universe. This black hole exists in a galaxy that formed just 1.5 billion years after the Big Bang, during a period when the universe was still in its cosmic infancy. The implications are staggering because if black holes could grow this rapidly in the early universe, it means our entire timeline of cosmic evolution might be completely wrong. But the rabbit hole goes much deeper when you start examining the truly bizarre properties of rotating black holes. Every black hole in the universe spins, and the fastest ones rotate at speeds that would make your head spin just thinking about them. The record holder, designated GRS 1915-105, completes over 1,000 full rotations every single second. To put that in perspective, if Earth rotated that fast, everything on the surface would be flung into space at thousands of miles per hour. When a black hole spins this rapidly, it doesn't just rotate in isolation. It literally drags the fabric of space-time around with it in a phenomenon called frame dragging. Imagine space-time as a thick fluid, and the spinning black hole as a massive paddle stirring through it. The rotation creates a region around the black hole called the ergosphere, where nothing can remain stationary relative to distant observers. Everything within this zone is forced to rotate along with the black hole, whether it wants to or not. This frame-dragging effect creates opportunities for energy extraction that seem to violate conservation of energy at first glance. Through a process called the Penrose mechanism, objects can actually fall into the ergosphere and emerge with more energy than they entered with, stealing rotational energy from the black hole itself. It's like cosmic theft, where the black hole is forced to give up some of its spin energy to anything clever enough to exploit this relativistic loophole. The monster black hole at the center of the galaxy M87 demonstrates this effect on a scale that's almost incomprehensible. This supermassive giant spins at 80% of the maximum possible rate allowed by physics, and its rotation powers jets of particles that extend for thousands of light years through space. These jets move at nearly the speed of light and contain more energy than thousands of galaxies combined, all powered by the rotational energy of a single spinning black hole. But here's where things get truly mind-bending. The rotation of a black hole fundamentally changes the shape of space-time itself. While non-rotating black holes create spherical event horizons, spinning black holes create oblate, flattened horizons that bulge at the equator. The faster the spin, the more distorted the horizon becomes, until at maximum rotation, the event horizon almost touches what's called the photon sphere, the closest stable orbit for light. This geometric distortion has profound implications for anything trying to orbit or fall into a rotating black hole. Objects approaching from different directions experience completely different gravitational effects. Material falling in along the spin axis behaves differently from material approaching along the equatorial plane. The rotation creates preferred directions in space, breaking the spherical symmetry that exists around non-spinning black holes. Recent observations have revealed that some supermassive black holes are spinning so fast they're approaching the theoretical maximum rotation rate allowed by general relativity. At this limit, called the extremal Kerr limit, the event horizon and ergosphere merge, creating exotic conditions where the laws of physics become even more twisted than usual. Some theoretical physicists speculate that black holes spinning faster than this limit might be possible, creating naked singularities where the bizarre physics of the black hole interior becomes visible to outside observers. Now let's explore something that will fundamentally change how you think about time itself. Near a black hole, time doesn't just slow down. It becomes completely relative in ways that create paradoxes your brain wasn't designed to handle. The closer you get to the event horizon, the more extreme these temporal distortions become, until something truly bizarre happens at the boundary itself. From the perspective of someone falling into a black hole, time appears to flow normally. You would cross the event horizon after a finite amount of time and continue falling toward the singularity at the center. But from the perspective of someone watching you fall from a safe distance, something completely different happens. They would see you slow down as you approach the event horizon, your movements becoming more and more sluggish until you appear to freeze completely at the boundary, never quite crossing over. This creates one of the most mind-bending paradoxes in physics. From your perspective, you fall through and continue your journey to the center. From an outside observer's perspective, you never cross the event horizon at all, instead appearing frozen at the edge of the black hole forever. Both perspectives are equally valid according to general relativity, yet they describe completely contradictory events. The paradox gets even weirder when you consider what happens to your image as seen by the outside observer. As you appear to slow down and freeze at the event horizon, your image would also begin to redshift, the light from your body stretching to longer and longer wavelengths until it fades into infrared and then radio waves. Eventually, you would become completely invisible, your frozen image disappearing from view, even though from the outside perspective you never actually crossed the event horizon. This temporal weirdness extends beyond just the event horizon. The region around a black hole creates a gradient of time dilation that varies dramatically with distance. A clock positioned just outside the Schwarzschild radius might record 1 year passing, while an observer light-years away would perceive that same period as approximately 141 years. This means that if you could somehow survive near a black hole's event horizon for what feels like a single day to you, centuries or millennia could pass in the outside universe. These extreme time dilation effects have practical implications that go far beyond theoretical physics. They represent a form of time travel that actually exists in our universe, not as science fiction but as measurable reality. Astronauts on the International Space Station experience time at a slightly different rate than people on Earth's surface due to the weaker gravitational field at their altitude. Near a black hole, these effects become so extreme that they could theoretically allow someone to travel far into the future in their own reference frame. But the most disturbing aspect of black hole time dilation is what it reveals about the nature of simultaneity itself. Events that appear simultaneous to one observer near a black hole might be separated by years or centuries from the perspective of someone farther away. This breakdown of universal time creates a universe where the concept of now becomes completely meaningless on cosmic scales. The study of these temporal effects has led to profound insights about the nature of information and causality in the universe. If someone falls into a black hole carrying information, that information appears to be preserved forever from an outside perspective, frozen at the event horizon. Yet from the faller's perspective, the information crosses over and is presumably destroyed at the singularity. This creates the black hole information paradox, one of the most important unsolved problems in theoretical physics. Recent theoretical work suggests that the resolution to this paradox might require us to completely reimagine how space and time work at the quantum level. Some physicists propose that the event horizon isn't actually a boundary at all, but rather an emergent property that only exists from certain perspectives. Others suggest that the interior of a black hole might be connected to distant regions of space-time through exotic structures called wormholes. These ideas push the boundaries of our understanding so far that they begin to resemble the wildest science fiction. Yet they emerge from rigorous mathematical analysis of Einstein's equations and quantum field theory. The universe near black holes operates according to rules so strange that even our most advanced theories struggle to make sense of them. The consequences of these temporal paradoxes become even more unsettling when you consider what happens during the formation of a black hole itself. When a massive star collapses, the process creates a cascade of increasingly bizarre effects that seem to violate our most basic assumptions about cause and effect. As the stellar core contracts past the Schwarzschild radius, the formation of the event horizon creates a boundary in space-time that fundamentally changes the causal structure of the universe. From the perspective of the collapsing matter, the formation happens in finite time. The stellar material continues falling inward, crossing what will become the event horizon and eventually reaching the central singularity. But from the perspective of outside observers, the event horizon never quite forms at all. They see the stellar surface approaching the critical radius but never quite reaching it, instead appearing to freeze and fade away into invisibility. This creates a profound puzzle about the very existence of black holes. If the event horizon never forms from an outside perspective, then how can black holes exist at all? The answer lies in understanding that the event horizon isn't a physical surface, but rather a coordinate-dependent boundary that exists differently for different observers. It's a feature of space-time geometry that emerges from the extreme curvature created by the concentrated mass. But here's where things get truly mind-bending. Recent theoretical work has suggested that the interior of a black hole might not exist in any meaningful sense until something actually crosses the event horizon. Some physicists propose that the black hole interior is created by the act of observation itself, emerging from quantum entanglement between the falling observer and the external universe. This idea leads to even more disturbing implications about the nature of reality. If the black hole interior doesn't exist until someone falls in, then what happens to all the matter that supposedly fell in before that moment? The mathematics suggests that this matter might exist in a superposition of states, neither inside nor outside the black hole until the quantum wave function collapses through observation. These quantum effects become even more pronounced when you consider the phenomenon of black hole complementarity. This principle suggests that information can simultaneously fall into a black hole and remain outside on the event horizon, existing in two contradictory states depending on who's observing. It's like a cosmic version of Schrödinger's cat, where the same information can be both destroyed and preserved until someone checks. The implications extend far beyond just black holes. If space-time itself can exist in quantum superposition near event horizons, then the entire fabric of reality might be far more malleable than we ever imagined. The universe might not be a fixed stage on which events unfold, but rather a dynamic system where the act of observation fundamentally shapes the structure of space and time itself. Recent discoveries have revealed that these quantum effects aren't just theoretical curiosities, but have measurable consequences for black hole behavior. Scientists have detected subtle correlations in the radiation emitted by black holes that suggest quantum entanglement between particles inside and outside the event horizon. These correlations persist across vast distances and appear to violate our understanding of how information can travel through space-time. The study of these quantum correlations has led to the development of holographic theories that describe black holes as two-dimensional surfaces that encode three-dimensional information. According to these models, everything that falls into a black hole leaves a holographic imprint on the event horizon, preserving the information in a highly scrambled form that can theoretically be reconstructed by outside observers. But the real shock comes when you realize that these holographic principles might apply to the entire universe. Some physicists now believe that all of reality might be a holographic projection from a two-dimensional surface at the cosmic horizon. This would mean that the three-dimensional world you experience, including your own body and consciousness, is actually encoded information on a distant boundary of space-time. These ideas sound like pure fantasy, but they emerge from rigorous analysis of black hole thermodynamics and quantum field theory. The mathematics is so compelling that it's forcing physicists to completely reconsider the fundamental nature of space, time, and information. We might be living in a universe that's far stranger and more interconnected than anyone ever imagined. The strangest part is that these quantum effects become more pronounced for smaller black holes. While supermassive black holes have relatively gentle tidal forces and calm event horizons, microscopic black holes would be seething with quantum activity. Near the event horizon of a tiny black hole, virtual particles would be constantly popping into existence and annihilating each other, creating a foam of space-time fluctuations that would make the vacuum itself unstable. This quantum foam represents the ultimate breakdown of our classical understanding of space and time. At these scales, the smooth geometry described by Einstein's equations dissolves into a chaotic sea of quantum fluctuations, where distance and duration lose their meaning. The event horizon becomes not a sharp boundary but a fuzzy region where quantum uncertainty makes it impossible to define exactly where space ends and the black hole begins. Some theoretical physicists have proposed that this quantum foam might be the source of dark energy, the mysterious force accelerating the expansion of the universe. If space-time itself is constantly bubbling with quantum black holes appearing and disappearing on microscopic scales, their collective effect might be pushing the universe apart. This would mean that black holes aren't just isolated objects in space, but fundamental components of the cosmic fabric itself. The search for these microscopic black holes represents one of the most ambitious experiments in modern physics. Scientists are using particle accelerators to create conditions extreme enough that tiny black holes might form and immediately evaporate, releasing characteristic patterns of radiation that would prove their existence. Finding even one such event would confirm some of the most exotic predictions of quantum gravity and potentially reveal new dimensions of space beyond the three we experience. But perhaps the most unsettling discovery about black holes is how they challenge our understanding of identity and continuity. When matter falls into a black hole, it becomes impossible to track individual particles or preserve distinct identities. Everything gets scrambled together in ways that seem to violate the fundamental principle that information cannot be destroyed. This scrambling process happens gradually as matter approaches the event horizon. The extreme tidal forces stretch and compress infalling objects, breaking apart molecular bonds and eventually atomic nuclei themselves. By the time anything reaches the event horizon, it has been completely disassembled into its constituent particles, losing all trace of its original structure and organization. Yet quantum mechanics insists that information must be preserved somehow. This creates the black hole information paradox, which has puzzled physicists for decades. The scrambling process appears to be irreversible, yet quantum theory demands that any process must theoretically be reversible given enough time and computational power. Recent theoretical breakthroughs suggest that the information might be preserved in quantum correlations that extend across the event horizon. As particles fall in, they become entangled with particles in the Hawking radiation being emitted, creating a web of quantum connections that spans the boundary between inside and outside. The information about what fell in would be encoded in these correlations, scrambled beyond recognition but theoretically recoverable. This process would take an almost incomprehensible amount of time. For a solar mass black hole, recovering the information about what fell in would require analyzing the Hawking radiation for longer than the current age of the universe multiplied by trillions of trillions. The information would be there, but extracting it would be practically impossible for any conceivable observer. The implications go beyond just black holes to touch on fundamental questions about consciousness and identity. If the information that makes up your thoughts and memories fell into a black hole, it would be preserved in principle but scrambled beyond any hope of reconstruction. You would effectively cease to exist as a coherent entity while simultaneously existing forever in the quantum correlations of the black hole's radiation. These philosophical implications become even more profound when you consider the ultimate fate of the universe. In the far distant future, after all the stars have burned out and only black holes remain, the cosmos will be dominated by these slowly evaporating remnants. The final era of the universe will be characterized by the gradual release of Hawking radiation as black holes convert their mass back into elementary particles over timescales that dwarf the current age of the universe. During this final epoch, the black holes will serve as the universe's last energy sources, providing the only illumination in an otherwise cold and empty cosmos. The largest supermassive black holes will outlive everything else, continuing to emit their faint radiation long after even protons have decayed and all other matter has disappeared. They will be the final witnesses to the universe's history, carrying within their quantum correlations the scrambled information of everything that ever existed. But even these cosmic survivors are not eternal. Eventually, through the slow process of Hawking evaporation, they too will disappear, releasing their stored information back into the void as elementary particles and photons. The final moments of the largest black holes will be spectacular as the evaporation process accelerates exponentially, culminating in brilliant flashes of gamma radiation that will briefly illuminate the empty cosmos before fading forever. The study of these ultimate endings has revealed something profound about the nature of time and entropy in the universe. Black holes represent the most efficient way to pack information into space, and their evaporation represents the universe's final attempt to maximize entropy and reach thermal equilibrium. In a sense, black holes are the universe's way of organizing its own death, concentrating all available energy into its most compact possible form, before slowly releasing it back into the void. This cosmic perspective reveals black holes not as destroyers but as transformers, taking the complex structures of stars, planets, and civilizations and converting them into their most fundamental components. They serve as cosmic recycling centers, breaking down the elaborate constructions of billions of years of evolution and returning their constituent particles to the primordial soup from which new structures might someday emerge. Yet even this recycling process is imperfect. Each time matter falls into a black hole and is later released as Hawking radiation, some of the original information is irretrievably scrambled. The universe gradually loses its ability to remember its own history, with each black hole evaporation representing a kind of cosmic amnesia that erases the details of what came before. This gradual erasure of cosmic memory leads us to one of the most disturbing implications about black holes that no textbook will ever tell you. The universe isn't just expanding and cooling toward a cold death. It's actively forgetting itself through black hole evaporation. Every time a black hole disappears in its final burst of radiation, it takes with it the scrambled quantum information of everything it ever consumed, leaving behind only the most basic particles with no memory of the complex structures they once formed. But here's where the story takes an even more unsettling turn. Recent theoretical work suggests that information erasure might not be the end of the story at all. Some physicists propose that the quantum correlations in Hawking radiation might actually create new structures in space-time itself, potentially giving birth to baby universes that branch off from our own reality. These daughter universes would inherit the quantum information from evaporating black holes, carrying forward the scrambled memory of our cosmos into entirely new realms of existence. This process would be completely invisible to us. As black holes evaporate, they might be secretly spawning countless new universes, each one inheriting a piece of our reality's history encoded in quantum fluctuations. The final gamma-ray burst from a dying black hole wouldn't just be the end of a cosmic giant, but potentially the birth cry of an entire new cosmos, complete with its own physics, its own space and time, and its own eventual black holes. The mathematical framework describing these baby universes emerges from string theory and quantum gravity, suggesting that our entire observable universe might itself be the product of a black hole evaporation in some parent cosmos. This would mean that everything you've ever known, every star in the sky, every planet and galaxy, exists inside what was once the interior of a black hole in a higher dimensional reality that we can never observe or interact with. Think about the implications of this for just a moment. Your entire existence, every thought you've ever had, every emotion and experience might be nothing more than quantum information processing inside a black hole that's slowly evaporating in some unimaginable parent universe. The atoms in your body, the neurons firing in your brain, the very consciousness reading these words right now. All of it could be elaborate patterns in the quantum foam of a dying cosmic giant. This brings us to something even more mind-bending about black hole formation that challenges everything you think you know about cause and effect. When scientists study the most distant galaxies, they're looking back in time toward the early universe, and what they've discovered there defies explanation. Fully formed supermassive black holes already existed when the universe was less than 1 billion years old. Black holes so massive they shouldn't have had enough time to grow from stellar remnants. The fastest growing black hole ever discovered exists in this early epoch, a monster designated as having a mass 17 billion times larger than our sun. This cosmic glutton consumes the equivalent of an entire sun every single day, creating an accretion disk 7 light-years wide that resembles a gigantic magnetic storm, with temperatures of 10,000 degrees Celsius, and winds that would circumnavigate Earth in a single second. The sheer scale of this feeding frenzy suggests that the early universe was far more violent and chaotic than anyone imagined. But what makes this discovery truly disturbing is the implication for cosmic evolution. if black holes could grow this rapidly in the universe's infancy. It suggests that the formation of large-scale structure happened much faster than our models predict. Entire galactic clusters might have assembled in just a few 100 million years after the Big Bang, compared to the billion-year timescales previously thought necessary. This accelerated evolution creates a cascade of consequences that ripple through our understanding of cosmic history. Star formation rates in the early universe must have been dramatically higher than expected, burning through available gas reservoirs at unprecedented rates. The first generation of stars, those massive primordial giants that forged the heavy elements necessary for planet formation, lived fast and died young in spectacular supernovae that seeded space with the building blocks of complexity. The violence of this early epoch would have been unimaginable. Gamma-ray bursts from hypernova explosions would have sterilized entire regions of space, preventing the formation of the first planetary systems. Only in the brief quiet periods between these cosmic catastrophes could the delicate processes of chemistry and biology begin to take hold. The emergence of life in such a hostile environment seems almost miraculous, suggesting that the universe's capacity for creating complexity is far more resilient than we ever suspected. Recent observations have revealed another layer of this cosmic violence that textbooks completely ignore. Some galaxies contain not just one supermassive black hole at their center, but multiple black holes orbiting each other in complex gravitational dances. These systems represent the aftermath of galactic mergers where entire galaxies collided and their central black holes became gravitationally bound to each other. The discovery of such binary and triple black hole systems reveals that galaxy formation was far more chaotic than previously thought. Rather than growing in isolation, galaxies repeatedly crashed into each other, with their central black holes eventually spiraling inward through a process called gravitational wave radiation. Each orbit brings them closer together while releasing ripples in space-time that carry away orbital energy, inexorably driving the black holes toward their ultimate merger. When supermassive black holes finally merge, they create gravitational wave events so powerful they shake the very fabric of space across billions of light years. The LIGO and Virgo detectors have already observed dozens of such mergers from stellar mass black holes, but the mergers of supermassive giants would create signals thousands of times stronger, detectable from the very edge of the observable universe. These merger events represent some of the most energetic phenomena possible in physics, converting several solar masses worth of material into pure gravitational wave energy in just a few seconds. The space-time distortions they create are so intense that they would be measurable even without sophisticated detectors, actually changing the length of meter sticks and the rate of atomic clocks in laboratory experiments. But here's the truly shocking part about these black hole mergers that no one talks about in school. The collision doesn't just combine two black holes into one larger object. The violent dynamics of the merger can actually kick the resulting black hole completely out of its host galaxy, sending it careening through intergalactic space at speeds of thousands of kilometers per second. These rogue black holes represent a completely hidden population of cosmic wanderers that drift through the void between galaxies, carrying with them the scrambled quantum information of everything they consumed before their violent ejection. Some estimates suggest there might be billions of these homeless black holes wandering through space, completely invisible except for their gravitational effects on any unfortunate matter that crosses their path. The existence of rogue black holes creates terrifying possibilities for cosmic catastrophe. If one of these wandering giants passed through our solar system, it wouldn't need to directly impact Earth to cause complete devastation. The gravitational perturbations would destabilize planetary orbits, potentially ejecting Earth from the solar system entirely, or sending it spiraling into the sun. Even a near miss by a rogue black hole would be catastrophic. The tidal forces would trigger massive earthquakes, volcanic eruptions, and tsunamis as Earth's crust flexed and buckled under the changing gravitational field. The atmosphere might be partially stripped away, while the magnetic field could be disrupted enough to allow lethal radiation from space to reach the surface. The probability of such an encounter is vanishingly small over human timescales, but over the billions of years of cosmic evolution, these events become statistically inevitable. The fossil record on Earth might actually contain evidence of past encounters with rogue black holes, hidden in mass extinction events that can't be explained by conventional causes like asteroid impacts or volcanic eruptions. This brings us to one of the most unsettling discoveries about black holes that will keep you awake at night. Scientists have found evidence that some black holes don't just wander randomly through space, but actually hunt for matter in surprisingly sophisticated ways. Observations of certain black hole systems show feeding patterns that suggest these cosmic predators can somehow detect and pursue sources of matter across vast distances. The mechanism behind this hunting behavior involves the complex interplay between a black hole's magnetic field and the surrounding plasma environment. As matter spirals into a black hole, it creates powerful magnetic field lines that extend far beyond the accretion disk. These field lines can channel material from much greater distances, essentially creating gravitational fishing lines that can snare passing gas clouds or even entire stars. Some black holes have been observed to completely devour star-forming regions, systematically consuming every available source of matter in their vicinity before moving on to hunt elsewhere. This predatory behavior can completely sterilize entire sectors of galaxies, creating vast dead zones where no new stars can form. The long-term effects of this cosmic predation might explain why some galaxies appear to have stopped forming stars entirely. Despite having abundant gas reserves, the hunting strategies employed by different black holes vary dramatically based on their mass and environment. Stellar mass black holes in binary systems can strip matter from their companion stars with surgical precision, while supermassive giants can orchestrate the disruption of entire globular clusters, feeding on hundreds of stars simultaneously in cosmic feeding frenzies that last for millions of years. Recent computer simulations have revealed that some black holes might even coordinate their feeding behavior with other black holes in their vicinity, creating networks of gravitational influence that can manipulate the flow of matter across entire galactic regions. This collective hunting behavior suggests a level of emergent complexity in black hole systems that resembles the coordinated behavior of living organisms, despite being purely gravitational phenomena. The implications of this discovery extend far beyond just astrophysics into fundamental questions about information processing and collective behavior in the universe. If black holes can exhibit coordinated hunting strategies, it suggests that gravitational systems might be capable of much more sophisticated behavior than previously imagined. The universe itself might contain forms of information processing and decision-making that operate on scales and timescales completely beyond human comprehension. This leads us to perhaps the most disturbing question of all about black holes. If these objects can process information, exhibit hunting behavior, and even coordinate with each other across vast distances, could they potentially be conscious in some sense? The idea sounds absurd at first, but it emerges from serious consideration of what consciousness actually requires at its most fundamental level. Consciousness appears to arise from information integration and processing within complex systems. If black holes are capable of storing and manipulating quantum information on cosmic scales, they might represent forms of consciousness that operate according to completely alien principles. Their thoughts would unfold over millions or billions of years, processing the quantum information of everything they consume into patterns of unimaginable complexity. So there you have it. The universe your teachers described was a pale shadow of the reality that actually surrounds us every moment. These cosmic giants aren't just distant curiosities, but active participants in a cosmic drama of unimaginable complexity, where the boundaries between destruction and creation, between matter and information, between past and future, blur into something that challenges our most fundamental assumptions about existence itself. The next time you look up at the night sky, remember that hidden in that darkness are objects so strange they would make your high school physics textbook spontaneously combust. Sweet dreams.